In today's lecture, we are going to discuss about realizing all the logical gates using NOR gate. So we have different logical gates like AND, OR, XOR, XNOR, NOT. So all these logical gates can be realized using two gates. One is NAND and another one is NOR. So this NAND and NOR, since with NAND and NOR, we can realize all the other gates. Those two are known as universal gates. Right? NAND and NOR gate are known as universal gates. Why so? Any gates, any other gates, and or not, XOR, XNOR, all these gates can be realized using NAND and NOT. That is why it is known as a universal gate. In a lecture already we have discussed about the realization of all the gates using NAND. In today's lecture we are going to discuss about realization of all the gates using NOR. So this is two input NOR. NOR is the inverse of OR. That is, if both the inputs are false, we'll be getting output. And this is three input NOR gate. Again, the case is if all the inputs are false, then we'll get the output in the case of NOR. So how to realize NOR as NOT? So if you see here, NOT gate is a single input gate. So but NOR is a two input gate. So I'm taking one input, that is NOT, the input of NOT, and then since I cannot give it as a single lead, I'm splitting it and I'm giving it into two leads. So here we'll be having X and then X again, right? So, it will be likewise. And so see here, this is an OR gate, and after this bubble it is NOR. So here X or X. Here this input is also X, this input is also X. It was written here X or X, that is X plus X, right? And for this bubble we have inserted a dash. So X plus X dash. So by the law it is equal to X plus X. By law it is equal to X, and so X dash. So see, the output is, if I give X as an input, the output is X dash, right? So when I give input as X and if I get an output X dash, what gate it is? It is NOT gate, right? But I haven't used a NOT gate here. I've used a NOR gate here. So we have realized the NOT operation using a NOR gate, right? The operation is NOT operation, but the gate what we have used is NOR gate. So this is realization of a NOT gate using NOR gate. And now coming to AND gate. Now if you see AND gate, right? We have two inputs for AND gate. X and Y are being considered. See, this X and Y is being given to as inputs to XNOR gates. Right? Since XNOR will not receive a single input, that single input is splitted into two and is being given to two terminals. Right? The output is given to another NOR gate. So these are the laws which we have used to achieve that. See, once after myself applying inversion to the inputs, and then again after XOR operation, if I take inversion again, so here we have used idempotent law, here we have used De Morgan's law. So here X and X here. So now see X, X, and the output is X plus X dash. This is again Y plus Y dash, and the output here will be X plus X dash plus, again it is an OR, X or NOR gate. So X plus X plus Y the whole dash, here it was written. This is the input. And after simplification, so for X plus X is written as X, and this dash inversion was mentioned here, this OR is mentioned here, Y plus Y by idempotent law it is Y, and so Y, and this inversion was mentioned here. Now we have applied De Morgan's law. Here we have another inversion. So if I apply De Morgan's law, the variables will be inverted. And so x, already we have x dash, and now again we are giving an inversion x double dash, and the r will change to and, plus will change to dot, right? And y double dash, x double dash is equal to x, y double dash is equal to y. Now you see here, this is the expression for AND gate. So we have realized AND using NOR gates. Again, OR gate, the same way we can realize OR gates also with the help of two NOR gates connected serially. This is NAND gate using NOR gate. Again, you see here the same idempotent involution and involution laws are being used. And now coming to XOR. So I've given the detailed expression here for an XOR gate, since it looks a bit complicated. It's not complicated. So this is my final XOR gate. So how it is being achieved with the help of XOR? See, I'm using OR gates. I'm taking inversions, right? My aim is to make this and this as OR. So see, accordingly apply inversions, right? Apply inversions and apply De Morgan's law. We'll get the XNOR as output. And this is XNOR using NOR, right? Here again we have applied a double inversion. We have taken double inversion. Then again we have applied De Morgan's law, and after that we'll be getting an XNOR gate. So this is the expression for XNOR gate. So the gates what is used, but we have realized this is the expression for XNOR. This is the circuit for XNOR, but we have realized using NOR gate. Thank you for watching, and this is fair assessment. Thank you.